a very few properties. Oh, should I start once again? No? Can you hear me?
No. It's okay.
It's okay. Okay. I will discuss very few properties of this Yangian. In fact, I will not discuss RTT presentation at all because I will not use it. After that, I will discuss the centralizer construction and the definition of the Yangian-type algebras, which I will denote by YD of A. I will give the definition and I will try to formulate some of the properties. To do that, I will need double Poisson brackets. In fact, I will need very specific double Poisson brackets on 3 algebras. I will give the main definition of the double Poisson brackets, which is due to Michael van den Berg. I will provide some examples and I will discuss links to these Yangian-type algebras. And if time permits, I will discuss something else. All right, let me start. Let me recall the definition of the Yangian of GLN. It is an associative algebra, associative unital, which is generated by the following elements, Tij, and with index r. I and j here are integers from 1 to n, where this n appears here, and r is a non-negative integer. We also agree that the 0th component is just the Kronecker delta. So it is just a constant. This algebra is generated by these elements with the following relations. With the following commutative with the following relations, right? Let me write them down explicitly. Hopefully I will not write many formulas in my talk, but this is one of them. So I hope that it is a well-known formula for some of the participants of this seminar. What properties of the Yangian I would like to discuss? Well, there are in fact 2 properties which I would like to generalize in a more general framework. And all of these properties are related to the fact that this Yangian is a filtered algebra. The first property is that the Yangian is a filtered algebra with respect to the following filtration. Then it's not very difficult to see then the associated graded algebra of the Yangian with respect to this filtration is commutative. Then on this associated graded algebra carries a natural Poisson bracket. And if we denote by TR bar IJ the element of this associated graded algebra, then the Poisson bracket is given by this. And here on the right-hand side, we should just put the right-hand side of the equation above. So it's not very interesting to discuss it in more details right now. I just want to mention that the Yangian has some filtration with respect to which the associated graded algebra is commutative and carries a natural Poisson bracket. The second property is related to a different filtration, the shifted filtration. This shifted filtration is defined as follows: R minus 1. So it is almost the same as the previous filtration, but it is a little bit shifted. Then the associative graded algebra is not commutative anymore. But if we look at this expression closer, in fact, we can see that these relations can be rewritten as follows. And plus some terms which are of the form of product of two terms. And due to this minus 1, if we consider this this formula in the associated graded with respect to this new filtration, then we can see, let me denote by T tilde the element of the associated graded algebra with respect to this shifted filtration. Then we see that the following relations hold. So we can see that these relations are exactly the relations of the algebra, of the universal enveloping algebra, of the polynomial currently algebra. So and my goal for today is to explain some analogs of these two properties in a more general setting for the Yangian-type algebras. All right, now I'm going to discuss the centralizer construction and the definition of these new Yangian-type algebras. And if you have any questions, please ask. Centralizer construction. Let me pick an algebra over C. And this curly A is an arbitrary algebra, which may be unital or non-unital. Then we can consider the Lie algebra of matrices over this A. I will denote it by GLD. No, I will denote by GLN of A. And the commutator is just the ordinary commutator, AB minus BA. Then we can consider, let me say that this algebra A is countably dimensional. So this GLN over A may be an infinite dimensional D algebra, but that will not be a problem for us. And we can consider its universal enveloping algebra. Olshanski's centralizer construction deals with some centralizers of the form like this. I will explain this notation just in a moment. And when we will have the definition of this centralizer, we will form some projective limit of them. Projective limit with respect to n, which is here and here. And this is going to be the algebra we will work with. So let me explain this step by step. Suppose first that A is unital. Then GLN over C over the complex numbers is embedded into this GLA, just because A contains 1. Then we have an action of GLN on this GLN of A, which is just the commutator. But in fact, if let me write this action down explicitly. So we take some x from here, and we take an element of this, which I denote like y of A, where y is a matrix. N times n, and A is an element of curly A. Then this action of x on this y of A is given by this formula. Where here and here we have just the ordinary matrix multiplication. But in fact, if A is not unital, then we can define the action of GLN on this GLN of A by the same formula. I'm explaining this just because I would like some subalgebra of this GLN to act on this universal enveloping algebra. And then I will take invariance of this action. So now we have GLN over C, which acts on this GLN over A. And we pick here a subalgebra, a Lie subalgebra, which consists of the following matrices. Here we have n minus d and n minus d, and here we have d and d. So this algebra, which I denote by GL sub d of n, is spanned by the matrix units whose indices are greater than d. And then we can consider this invariance. The only thing that remains to explain is the projections. So let me denote this invariance by an. Of course, this guy also depends on D. So this guy depends on D as well. And I forgot to say that D is just a natural number which is fixed once and for all. All right, projections. Now I'm going to describe projections like this. How can I do that? Let me do this on the next slide. I'd like to have these formulas on that slide. Projections. Okay, for that I need some notation. I plus is the left ideal of our matrix algebra over A generated by these elements. So it is generated by IN. Right, it is generated by IN of A. One more ideal which I would like to consider is a left ideal, or is a right ideal of the same algebra. I'm sorry. I should say here universal enveloping of that Lie algebra. And this ideal is generated by these elements. Then I propose you to do a small exercise on PDD filtrations of the universal enveloping algebra, which I wouldn't like to do right now. And the exercise is to check that the following equality holds. Oops. So here we take not the whole invariance we're interested in, but we take all the elements of this universal enveloping algebra that commute with this with the last unit, with the last matrix unit. Then we intersect this guy with our ideals, and these intersections coincide. And the main feature of this formula is that on the left-hand side we have a left ideal on the universal enveloping algebra of this, and on the right-hand side, this guy is a left ideal of this algebra, of course, and this guy is a right ideal because I minus is the right ideal, but they coincide. So these two guys, I will denote them by L of n, and this L of n is a two-sided ideal. And this two-sided ideal is going to help us to form these projections. Namely, it's not very difficult to check that this algebra itself can be splitted in the direct sum just as vector spaces. Of these two vector spaces. So it's not very difficult because you see this part is absolutely obvious, because if we have some smaller matrix, then it must commute with the last matrix unit, and the remaining part is this L of n. And in fact, this Pn, this our projection, is going to be the projection along this two-sided ideal. Since L of n is a two-sided ideal, this Pn is a morphism of algebras. So let me say this a little bit more clearly. We have constructed a morphism of algebras like this, -1. And then we can restrict it to the subalgebra of the whole of this invariance. And this projection along Ln will land in this invariance. Just because if we take an element which is invariant under this action, it will after the projection along the Ln, it will be invariant as well. So this guy is Pn. And now we have our algebras, An, and we have projections. Then we can form the projective limit of these algebras under these projections. And in this projective limit, in fact, we would like to consider a subalgebra, which will be denoted by yd of A, and it is going to be a Yangian-type algebra. But before saying that, I would like to consider a special case when this A is just the field. This case corresponds to the ordinary Yangian, just by the original version of Olshanski's centralizer construction. Can you still hear me?
Отлично.
Oh, okay, thank you. Yangian of GLD. And this Yangian, just the ordinary Yangian, it is generated by some elements of this projective limit. And now I would like to specify these elements. Or maybe I should use another slide. These elements, I will denote them by Tij of R, because it will be convenient for me. And these elements are as follows. We have the matrix E, which I define in a second. We consider this, and then minus R. So let me explain what it's written here. This matrix A this matrix E, it is just a matrix of Eij. So this matrix consists of Eij, where each Eij is an element of the universal enveloping algebra, GLN. Over C, of course, because we agreed that curly A is C for some time. So we have this matrix E. Then we divide it by U plus N. N is a natural number, which is here. And this U is just a formal parameter. After we have this guy, we can take its inverse, because it is a formal power series. Yeah, I should have said that we consider this as a formal power series in U minus 1. And we expand this power series. And in fact, we can take its inverse. It's invertible. Then we obtain some matrix. We take ij element of that matrix. So this guy is an element. Probably I should have written here matrices as well, right? Then this guy is an element of this power series. And the last thing we should do is to take its coefficient with respect to the minus r component. And this element is just Tij of r. So the main thing that I would like to say here, that the Yangian of GLD, as a subalgebra of this projective limit, it is generated by these elements. And in fact, for the general case, when this curly A is arbitrary, you can produce some elements of that projective limit very similar to these elements. But in fact, I wouldn't like to write them down explicitly because I will not use them. But what I want to do is to say something about their top degree. Concerning this case, when this curly A is just the field, the top degree can be explicitly written, and it's not a big deal. In fact, it is of the form. Oh, I'm sorry. Now I'm going to write down one more pretty big formula. And here we take the sum over all pi's, which range from 1 to n, and plus some lower terms. Lower terms, by this I mean lower terms in the sense of the PBW filtration. So that was all that I would like to say about this special case when A is just the field. Maybe it's worth to mention that another particular case when A is the product of fields was considered in a paper by Grigori Olshanski. And this case was considered in full details in that paper. And for this case, it is possible to produce a formula similar to this one. In fact, roughly speaking, in this case, when we take C to the L, we should modify this formula here. We should here put a sum over some index alpha. And we should consider formal power series in many variables. So we have index alpha here. We have different parameters, u sub alpha. And this matrix is also going to be split into L copies. All right, now I would like to say some words. I will not give an explicit definition of the elements of analogs of these elements Tij for the general case when curly A is arbitrary. But I will write down the top degree term. Maybe it would be good to formulate this as a definition. This Yangian-type algebra is unital, associative algebra, generated by the following elements. By the elements of this form. Tij of alpha. Here alpha is an element of the tensor algebra, which is just C plus A squared, and so on. So it is just the free algebra generated by the vector space A. Here I would like to assume that this alpha is a decomposable tensor. So it is of the form like this, where this AI belongs to A. And this is not a very rigorous definition, because I will say that we can produce some elements of that projective limit of the following form. The sum is exactly the same as before, and the only modification is here. Plus some low degree terms. So the difference between this formula and that formula that I've written before is that we have here our elements of our algebra A, which are packed into this tensor alpha. And this is the main definition for my talk. Now I would like to state some properties of this YD of A. The first property is related to the shifted filtration, because, as I said in the beginning, I'm going to generalize the two properties related to two filtrations of the ordinary Yangian to this more general framework. Let me state this as a theorem. (2023). It is a recent paper. This theorem says that the Yangian-type algebra YD of A is a filtered algebra with respect to the shifted filtration. I forgot to say right here that these indices ij, of course, they range from 1 to d. Yeah, so the degree of the generators of this algebra is just the degree of alpha and -1, because it is a shifted filtration. And the degree of alpha is just degree of an element in this tensor algebra. And since this algebra is filtered, we can consider its associated graded algebra. And it's going to be a universal enveloping algebra of some Lie algebra. This Lie algebra is a matrix Lie algebra, GLD, over some ring. Oh, this ring is denoted by R of A, and it is as follows. It's almost the tensor algebra of A, but not exactly. Meaning that it doesn't have constants. So and this algebra R of A may be non-unital, because as you can see here, we do not have here the field. This is just as a vector space. So R of A is A plus I squared plus etc. And the multiplication in this algebra is defined as follows. Right. Yeah. We take an element here, which is A1, etc., AN. Let us consider decomposable tensors. And here we take B1, etc., BM. So we take these two guys and send them to this pretty nice element, and AN minus 1. Then we take the last component of the first element, and the last component of the first element, and the first component of the second element. And we glue them together. By which, by this, I mean that we take the product in A. So this guy belongs to curly A, because A is an algebra. So this is the product in this R of A. I should put here a remark, which in fact states that this R of A is not very exotic. Suppose that the curly A is unital. Then this R of A is isomorphic to a free algebra, which I will denote by this. So let me explain what is written here. Here we take the product of A and A over C, of course. I emphasize here that we take this product over C because we will take in a minute some other tensor products over A, in fact. So we take this A times A and take some free algebra over it. Let me explain this. Let me denote by M this A times A. It is a bimodal. A. Because we can multiply elements of this guy by elements of curly A, of course, from left and from right. So this M is an A bimodal. And for this bimodal m, we can consider the following guy, which is a plus m times m over a. It is possible to consider this tensor product because m is a bimodule, and so on. So this is some sort of a free algebra. And this guy I denote just by this symbol. And let me just explain how this multiplication in A appears in this construction. It is due to the following fact. If we consider m times a, m over a, then it's just which is a cubed, of course, right? Because we can take this number, we can take this element and put it here due to this a linearity. And when we put it here, then we must multiply the element that was written here and this element. So this is the way how this multiplication appears in this construction. All right. That's all that I wanted to say about the shifted filtration in this new framework. Now I would like to say some words about the other filtration, which is not shifted. But for that, I need to discuss double Poisson brackets and to consider several examples of that double Poisson brackets on free algebras. Probably I have 15 minutes, right? Do I have only 15 minutes or a little bit more?
Yeah, actually 15.
Actually 15. Okay. So let me discuss double Poisson brackets very briefly. Let A be an associative algebra. By a double Poisson bracket is a linear map, which is denoted by this nice symbol. These double Poisson brackets were invented by Michael van den Berg. In his paper 2004, which is named Double Poisson Algebras. And a double Poisson bracket is such a bilinear map that satisfies the following properties. The first one is an analog of the skew commutativity. Here, this circle means that we must swap two tensor factors. The second property is some sort of Leibniz rule. Here, of course, A and B are elements of this A. And the second property is the double Jacobi identity. which can be read. Oh, I haven't said what this notation means. Here, this double bracket of A and B is an element of the tensor square of A, and we multiply it by C from right. So this means that if we multiply some element of the tensor square from right, then we just put this C onto the right factor. And the double Jacobi identity is as follows. So here on the left-hand side of this double Jacobi identity, we have an element of A cubed, because here we have this internal bracket is an element of the tensor square, and then this notation L means that we put this bracket to the left factor of this tensor square, and so we get an element of the tensor cube. So let me write this down as and this 1, 2, 3, which appears here and here, it is just the permutation of the factors in the tensor cube that pushes everything to the right. So it is a cyclic permutation that pushes everything to the right. All right. This is the general definition of double Poisson brackets due to Vandenberg. Now I would like to provide several examples and state our main theorem about these double Poisson brackets and Yangian-type algebras. There will be only 2 examples. The first one is pretty simple. We take as A the polynomial algebra in one variable, and we define the double bracket as follows. So in fact, this guy is not 0, unlike for ordinary Poisson brackets, because this skew commutativity, it's not the ordinary skew commutativity due to this swap of tensor factors. It's not very difficult to check that it's indeed double Poisson bracket, but I would like to present you an expression for this double Poisson bracket, double Poisson bracket on these 2 elements, because here we define this double Poisson bracket on the generator of this algebra, and then we can easily extend this to the whole algebra just by the Leibniz rule. It is a pretty easy exercise to compute the double Poisson bracket on these 2 elements. And it is as follows. And here you can see that this double Poisson bracket is very closely related to the Yangian GLN, because as you remember, there was the commutation relation like this with some right-hand side. And this right-hand side here, it can be how to say, deduced from this formula just by inserting indices on these guys, on every of these guys. So if we assign these guys indices like kj here, il here, and the same here, kj il. And of course, if we change x to the I-1 kj by t of a-1 kj, then we obtain exactly this right-hand side of the commutation relations in this Yangian GLN. So this expression should be familiar to those of the participants who know this Yangian GLN. But for my purposes, I need a more general Poisson bracket. This Poisson bracket is going to live on the free algebra T of A. And this Poisson bracket is defined as follows. Here I would like to put this boxed tensor product in order to distinguish it from the ordinary tensor product that lives inside the free algebra. And here we have the multiplication in A, in curly A. It is a very special double Poisson bracket because the right-hand side lives in this vector space. All the double Poisson brackets with such a property that on the free algebra, of course, such that the bracket of two generators lives in this vector space were classified by Pichero and Van de Veer in 2008. And in fact, all such Poisson brackets are classified by multiplications on the vector space. So this double Poisson bracket is a general double Poisson bracket in the class of this linear double Poisson brackets. And I have only 5 minutes left, so it's time to state the main theorem. And this theorem is a link between double Poisson brackets and Yangian-type algebras. This theorem states that the Yangian-type algebra is a filtered algebra with respect to the ordinary filtration. The first point. The next point is that the associative graded algebra of this filtered algebra is commutative. And the third point, the last but not the least, it explains how to compute the Poisson bracket, the natural Poisson bracket on this algebra in terms of the double Poisson bracket that I have just discussed. So let Tij of alpha be the corresponding element of the associated graded algebra. And we take the Poisson bracket of these two guys, where alpha and beta are some elements of the free algebra. Then we should do as follows. Let me put it in this way. So what is happening here? Here we have alpha and beta, which are elements of the free algebra. And we have that Poisson bracket on the free algebra. And we can compute this Poisson bracket on these two elements, alpha and beta. Then, when we computed it, we write it in Swidler's notation, in fact. So we have this x prime and x double prime. They live in the tensor algebra. And then this guy is by definition this. So we have an element of the square of our tensor algebra, which is this. And then we would like to put on each of that factors that indices kj and il, and produce an element of this associated graded algebra. That's exactly what is done here. So I think it's good time to stop here. If you have any questions, please ask. Thank you very much.
Okay, thank you for your talk. Any questions from the Zoom or from audience?
Nikita, can I ask you a question? Just
yes, sure.
Generic. And if you add the quadratic terms to these double brackets, it means that there are some R-matrix double Poisson brackets which add to these linear brackets. You don't have on this Yangian side a structure which corresponds.
Unfortunately not, because in fact we have some elements of this Yangian-type algebra. Then we compute this bracket, and it just appears to be of this type. It's not pretty clear.
This I understand, but my question was: is it possible to change the structure to enrich the structure in such a way that on the
double Poisson bracket becomes quadratic, but not only linear? Yeah, I understand this question, but it's not clear how to do this. It's not clear. It's not clear if it's possible. I think it's not possible, but
in principle, it was not possible in principle. That's what interesting, because if you add some R-matrix, well, classical R-matrix type double brackets, which correspond to, for example,
but that R-matrix is going to be associative, so it must satisfy the associative Yann-Baxter equation, right?
Yeah, but combination, namely combination with, is it possible? Maybe no. I don't know. On the quantum side, I mean, is it possible on the quantum side to define a structure similar to this Yangians, just like analog of, in some sense, universal enveloping affine quantum?
It is a very interesting question. It's indeed an interesting question. I need to think about it.
Okay, thank you. Very clear talks. Thank you.
Thank you very much.
Okay, thank you, Nikita. Any other questions? If not, let's send Nikita again.
Thank you very much.
Okay. Thank you all. The next week will be without seminar because we have public holidays in China. Okay.
Thank you.
Bye.
Bye-bye. Thank you.